In many environments, robots face obstacles that might catch or entangle them. Improving robot locomotion controllers to detect and circumvent these obstacles enables robots to operate in complicated scenarios. Brush and vines fill many natural environments. Here, it is not feasible to simply avoid contact with any solid object. Progress is usually made by pushing aside flexible plants. While a wheeled or tracked robot might crush these out of the way, legged robots could pick their way through them, causing less damage overall, as long as they have the ability to free themselves if they get stuck. This careful disentanglement would likewise serve robots well in cluttered artificial environments with cables, nets, or hoses. However, conventional legged robot controllers quickly get stuck on obstacles like vines or cords. Simple open-loop modifications like increasing step height or reversing the robot's joint directions still get stuck as well. Well-engineered swing-leg trajectories can clear high obstacles, but the dramatic motion is energetically costly, approximately doubling the power draw compared to the standard gait. To tackle this problem, we develop sensing and control for legged reversal of entanglements. We focus on simple forward motion through obstacles like plants or cords that could have different stiffness, damping, and friction. For simplicity, we assume that there is a simple hard and flat substrate beneath obstacles to provide secure footing. Since some obstacles may be easy to displace while others may be too strong, our approach first aims to proprioceptively detect large forces resisting a limb's advance. Taking advantage of quasi-direct drive actuation's high transparency, we can estimate joint torques induced by obstacles using the already existing motor measurements of a commercial off-the-shelf robot. Once the robot detects entanglement, a simple strategy aims to slide obstructions off the limb so that it can advance. We base our proprioceptive force sensing on a momentum-based observer with some modifications. First, since the ground reaction force with the foot is much higher on the ground than it is in the air, we reinitialize the momentum observer at foot liftoff. This enables more rapid detection of obstacles. The momentum-based observer allows the robot to ignore insignificant obstructions that can be easily pushed through. Here, when the robot breaks a thin wire, the measured hip torque never exceeds an experimentally found threshold of 2.5 Newton-meters. In contrast, an obstacle that does impede the robot's progress exerts higher force and exceeds the 2.5 Newton-meter hip torque threshold. Once this significant obstacle is detected by the momentum observer, the robot can try to disentangle itself. An entangled swing leg should first attempt to free itself from an obstacle by rising over it and sliding any entangling contacts off. This can be achieved by pulling the foot upwards with front surfaces sloped down. Applying a light forward force allows the robot to maintain contact with the obstacle until the leg is clear of the top. Once this occurs, the momentum-based observer detects loss of contact as the external joint torques drop to zero. When the robot detects that its leg is free, or if the time span of the current stride nears the end, the robot needs to put its foot down. To prevent recatching entanglements, the foot advances forwards at its current height until it is directly over the desired foothold, and then it descends. This motion keeps contact with most obstacles on the rear surface of the limb instead of the front, so that they do not impede the forward strides. Our strategy allows the robot to detect forces from obstacles and react once they rise to a level that impedes forward progress. It can handle obstacles of varying stiffness, from soft bungee cords to stiff ropes, and even rigid metal beams. Our strategy was successful in 12 out of 12 trials, and used less power than the aggressive open-loop strategy by selectively reacting only when obstructed. We tested our strategy outside of the laboratory in a bed of vines 8 centimeters high and compared it to a default controller as a baseline. While the default controller became entangled and fell over immediately, our controller walked for several body lengths before falling down due to low-performance camera-based state estimation. Future work will integrate more capable state estimation for outdoor experiments. In summary, we present legged robot entanglement detection and reaction to allow a commercial quadruped robot to push through and step over obstacles of varying stiffness and geometry. We hope that this work leads the way to legged robots more capable of handling unexpected contact with the environment to navigate cluttered real-life scenarios in natural and artificial environments. Thank you for your attention.